to bring back here. Not only were they here before, but they make a great kind of adventure food, grab and go. And that's why miners liked them. They could take them in the morning, they're hot, shove them in their pocket. They would actually take them and warm them up on a shovel using their headlamp and eat them over the course of the day. So it's a great historical food. It's a great adventure food. And I just decided to jump into the restaurant business and start a pasty shop in downtown Salt Lake called the Dough Miner. We have other things too, but pasties are what we're all about. So we'd love for y'all to stop in sometime and visit us.
Sure. Well, thanks, Ken.
Thank you.
And if you want to stay, I'll grab you a chair.
I got a restaurant.
Thanks so much. And go down and check out the Dough Miner. It's worth the stop. You stop once, I guarantee you'll stop more times after that. So I don't see Dee Theodore here, and I think she's coming, so I'm going to wait. We do have a letter that some of you signed it already. We're making one final push. The letter's going to go to the governor and to the speaker and to the president, just on this forest management concept of increasing our water and our forest health, the urban wildfire interface. Anyway, there's a big movement going there. Chad Booth has been pretty involved with helping to promote some of that. Anyway, it's a really big deal for Utah, and so we want to make sure that we get behind that. Scott, do you want to, Representative Chu, do you want to say?
So you guys, I've got that. I appreciate the attention of everybody, and this is my first time this year, but I've been here numerous times in the past. I was online last time. So I have a bill. As we all know, we're fed up with executive orders, and when the executive orders don't happen, we get rules made. And just like what's happening with the waters of the U.S. coming back and some of those kind of things. I've got a bill, it's 145, it's getting held up because 145 says that our agencies can't mandate a program on guaranteeing public access to private property. And I've had to narrow it down to Division of Wildlife because of some of their current proposals. And I just want to be sure that if you're contact your legislator, tell them, let's get 145 out of the rules. So that's where I'm at on it. Thanks. Appreciate that, Bill.
Thank you, Representative. I know if this table was in the back, people would probably be getting up and getting breakfast, but don't feel bashful to come up. So a few years ago, I was county commissioner, and I was involved with the 7-County Coalition, and which is a group of counties kind of in the south and the east and Uinta County, and we had some really good infrastructure development projects, a lot of it in the basin, centered around the railroad and some of these big projects that we were working on. One of the presenters that came to that at one point was Dr. Matt Memmott and from BYU, and really kind of spun our heads off with some of the technology. I'm big on anything nuclear. I'm from San Juan County. Our counties are nuclear. Kane County. We love coal too, Senator Hankins. And so anyway, Dr. Memmett's here. Dr. Fry's here. Appreciate Commissioner Siderud for putting this together. He was on that committee as well, 7-County Coalition. And so I asked him if he would come up today and talk about the San Rafael Research Center. And so I'm going to turn the meeting over to him. Towards the end, if John Bennett here, I might take a few minutes at the end, but otherwise, Lynn,
I'm not going to talk very long.
Lynn, I'm going to turn it over to you. Then you can organize how you want to do it.
All right, we appreciate being here today. Like Phil said, Dr. Memmott came 5 years ago and made a presentation at 7-County Infrastructure Coalition, telling us that we needed a research facility in Utah or in the West here, that the universities and the companies that were needing to do research on nuclear and other energy research, if they went to a national lab, it was taking, they would go through and wait their turn to do an experiment. And then when they finished that phase of the experiment, they would have to go to the back of the line and wait 2 or 3 or 4 months again to do the next phase of their experiment. And they were there for years, and they were paying a lot of money to do their research. And Dr. Memmott convinced us at 7 County that there needed to be a research facility in our area. And so everyone at 7 County Infrastructure Coalition agreed that we needed to do one within our 7 counties. Emory County was lucky enough that we had a piece of property and a building that had been vacated by a mining company. And we were able to pick that up and take off running. And so the rest of the 6 counties in the coalition supported, the 5 counties supported Carbon and Emory. Carbon's very well involved in this also. So they supported Carbon and Emory County in starting this research center. So what we've done is taken that old mining warehouse, converted it to nuclear research labs. And Dr. Memmott in a moment will explain to you what we're doing there. And we went out back in the storage sheds in the back and converted them to a building. University of Utah had a piece of equipment up here that had been used extensively for doing combustion experiments. We were able to purchase that piece of equipment, move it down also, and that allowed us to bring Dr. Fry in from BYU also. And Dr. Fry oversees the back half of the research center down there doing combustion research, while Dr. Memmott oversees us doing the nuclear research. And so we've had a lot of support from the state up to this point, most of it from CIB, but a lot from the state. We're requesting a little bit more from the state this year to keep things rolling as they have been. For as far as something that's government, it's come together really quick down there. Usually government works slow, but this research center has really came about pretty quick. And we appreciate all of the support that we've had in previous years. We've got 2 requests in this year. One for some match money for some equipment that Congressman Curtis was able to get us, and we just need some match to cover the match on it, and then some to help keep the last of our equipment and some employees in the facility down there. So I've got Commissioner Leonard here with me today from Emory County, and I've got Dr. Memmott and Dr. Fry. And what I'd like to do is just turn the time over to Dr. Fry and then Dr. Memmott and let them tell you what we're doing down there and why it's important to Utah and to the country and to the world. And then if there's any time left, we can add a little bit to it. I'd also like to mention how much Senator Hinkins has meant to the facility down there. He lives just down the road from it and has spent a lot of time there with us and has been a big supporter. So, Dr. Fry.
Thank you all for having me. It's good to be here. I'm excited to talk about the Centerville Energy Research Center. It's been a big part of what I've been doing for the last 5 years. And I'm excited to tell you about the things that we're working on. Professors like to have slides, so this is where we're going to talk for a minute. I thought I'd just give you a little bit of a background about me so you know why I'm interested in what I'm interested in. I came out of high school and swore I would never go back to school. I was done with that. And I went actually and worked at power plants in the center of Utah, both Huntington and Hunter power plants for about 3.5 years. And then for another 3.5 years, I worked industrial construction. And during that period, I really learned why energy is so important to us as a society. And I learned what it really takes to make power. And I knew I was interested in that field, but I didn't want to be at the bottom end of the totem pole anymore. So I went back to school and I knew that I wanted an advanced degree. So I went all the way through PhD, which I did at University of Utah, graduated in 2006. And then I wasn't at that time interested in academia, wanted to work in the power industry. And I went to work for a consulting firm here in Salt Lake City, Reaction Engineering International. I did that for about 7 years and then it got pulled back into academia at the University of Utah. And now I'm at BYU. Now, Matt will tell you, say that again?
Go Cougs.
Go Cougs. Matt will tell you shortly that I work on caveman technology and he works on the new stuff. And that might be true. We burn things for all of humanity's existence. But I propose to you that the fossil fuels are still important and they will be important into the future. And I embrace all of the new stuff that Matt's talking about, and I can't wait for him to retire me, but I don't think it's going to happen soon. So what I'm going to talk about, when we talk about fossil fuels, there's really two things that you can do with fossil fuels. You could burn them and use that heat energy to make power, or you can gasify them to convert them into other types of fuels. And that usually means we're taking solid fuels like coal or wood or something else and turning them into something else. And that could be natural gas, hydrogen, char, whatever. So I'm going to talk about the facilities that we've generated to do both of those types of technologies and the programs that we're working on. And some of them are really exciting. So the first section, combustion, it centers around the piece of equipment that Lynn talked about that we got from the University of Utah. I actually kind of brought it with me when I left University of Utah. They weren't that interested in keeping it. And then when we talk about gasification, we're going to talk about some new facilities that we're developing. So let's get going. Combustion. So if you don't know, and if you're not familiar with it, this is where the facility is. It's in Orangeville, Utah. That is a satellite image of the facility, and this is kind of the buildings that Lynn was talking about. This one right here is the nuclear building, and this is where we're putting all the combustion equipment. So in that combustion equipment building, it's been rehabilitated, and inside we have this large combustor that's called the L1500.
Hi.
We that piece of equipment was built in the mid-90s by a bunch of smart people from MIT and from some of the big power companies and consortiums in California. And it was built to mimic the type of power plants that we have in both Delta and in Emery County. And it allows us to do evaluations of new technologies and alternate fuels without actually trying them at the power plant. And it mimics those power plants really well. It's a large piece of equipment. It's hard to maintain it at universities. So it's wonderful to have a facility like this where we can run big programs and big equipment that are relevant for industry. And you're going to see that that's true here shortly. And this is what a flame looks like in that facility. You can do it. And maybe it won't show the video, but that's a coal flame. That's a coal flame under special conditions called oxycombustion. Oxycombustion actually can lead to zero emission coal-fired power plants. And you think, oh, that's crazy. That's pie in the sky. That's something that we already can do. We have the technology for it. It's been demonstrated in Germany and in Australia. It's just a little bit more expensive, so we haven't committed to it yet. So part of our research is to make things like that cheaper and more efficient. So we're going to talk a little bit about the programs that are running in this combustor right now. It was installed, probably began installing about 4 years ago. And we've already run many commercial projects and some government projects through the facility. So first, I'm going to talk about supercritical CO2 power cycles. And I don't want to wax too technical, but I want to help you understand something that you have been introduced to since you were in elementary school. The way that we make power right now from any, oh, here you go, from any thermal energy source. So whether we're burning coal, whether we're burning natural gas, it could be geothermal, it could even be nuclear. We use what's called the Rankine cycle. And you know what that is. You just don't know you know what that is. When you were first introduced to it, we talk about, well, we burn something to heat water to make steam. And then that steam drives a turbine and a turbine drives a generator. That's the Rankine cycle. And it's pictured right here. So I have a boiler that makes steam. It drives a turbine, and then we condense that water again and we pump it around in a circle. And this is what it looks like on a pH diagram. And I don't expect you to understand it all, and it's fine, but this right here represents the vapor dome. This is where we have a mixture of water and steam. And over here we have steam, and over here we have water. And we intersect that a lot, and it just means that we're going back and forth between steam. And there's a problem with this cycle. And the problem is that we reject most of the heat down here in this condenser. And it's at such a low temperature that we can't do anything with it. It's not usable. And that's what makes this process inefficient. Well, it turns out that there's other cycles that we could use that bypass that and allow us to get to much higher efficiencies. And one of those is to use supercritical CO2 in a cycle like this, where we're way above the vapor dome. And it adds a little bit of equipment and a little bit of complication, but we can get almost 10% better efficiency. And this is a really exciting technology because it doesn't just apply to coal. The nuclear people are just as excited about it, and it will be in all future power plants. But there's a lot that we don't understand about it yet, and we don't know how to deploy it at large scale. So I got a consortium of people, and we decided, let's get some government funding. We got about $5.5 million from the Department of Energy to prove this at a large scale. And essentially what we're doing is building a power plant at the San Rafael Energy Research Center. We are converting that L1500 combustor into a small power plant. And so we ripped it apart and we added different heat transfer surfaces. That's what these are. And they're made out of special materials that can handle the supercritical CO2 at the pressures and temperatures that it needs to be at. And we installed outside all kinds of equipment that represent the turbine and the compressors and the heat exchangers. And we just finished construction, and we're in the process right now of reviewing our safety issues so that we can start shakedown and testing and proving this technology. And we're really excited for that capability at the facility, because now that we have all the equipment in place, when we're done testing it on coal, we can turn around and start testing it on other technologies like nuclear. So we do play back and forth across the fence as well. So another thing that facility is really useful for is coal's kind of been under attack for a little while. And whether or not we like coal, there are some issues that we're struggling with even in this state. Our power plants are having a hard time getting enough coal right now. And there's a whole bunch of reasons for that, and I won't go into those reasons, but they're interested in alternate fuels. Some of those might be biomass, some of those might be refuse fuels of other types. But whenever you change fuels in a power plant like that, you run the risk of fouling heat transfer surfaces or changing the heat release profile so it doesn't work correctly. So as power plant operators don't like to just try a new fuel. They need to test it first. And so they come to a facility like we have at the San Rafael Energy Center, and they test the fuels. And one really interesting application of that technology in this state right now is our national forests in the state are sick. There's areas where 70% of the trees are dead because of bark beetle. And that causes wildland fire risk, and it's just not good for the environment. So we could harvest these materials, convert them into a coal-like fuel and put them in power plants. And we've done a lot of research on that. And so far, there's a couple of things that we look at. How does the fuel behave in the preparation equipment of the power plant? And this is equipment down at the facility that represents the coal mill and the coal handling system. And we can put all kinds of fuels through that and see how they behave and see if they're going to convert in the way that we need them to in order to have good combustion. And then we look at the combustion itself, and primarily we look at what happens to the ash, what happens to the mineral matter in the boiler, because that mineral matter can really screw up your heat transfer surfaces if the chemistry isn't just quite right. And this is a powerful tool, so much so that we've been doing work for Drax Power Station in the United Kingdom. This is a company that has taken a power plant about the size of IPP down in Delta and converted it from coal all the way to 100% biomass firing. And to do that, they have to pull fuels from all over the world. And so they get various types of fuels with weird chemistries and they have to test them before they go into their boiler. And they've come use this facility. We've also already run some tests for Rocky Mountain Power to investigate using that bark beetle biomass in our coal-fired boilers. And now they're interested in some other alternate fuels and we're in negotiations to do additional testing for them. So it's a really powerful piece of equipment for utilities and even our local utilities.
Can I ask you a question on
Yeah,
that?
absolutely.
So do you see quite a bit of difference between tree species in how they burn?
So that's a good question. So we could say softwoods, hardwoods, things like that. Yeah, there's a little bit of difference, but mostly in heating value, but not so much in ash chemistry. So it doesn't pose much of a difficulty to go between species. You get into the weird chemistry when you're talking about sustainable, fast growing crops. And that makes things hard. And that's a big interest right now too. And there's some, I guess, startup funding that's available that people really want to take small coal-fired power plants and say, can we turn these into sustainable combustors by putting fast growing crops in there? And we're going to develop some programs shortly.
Thanks.
Those fast growing crops, you're talking about sweetgrass and
Yeah, it could be switchgrass, miscanthus. There's some other things like that.
DJ.
Oh, yeah. So that's an issue here in Utah. We absolutely could handle that. But we would want to look carefully at the chemistry to see if that we needed to adjust anything to go in a boiler. But yeah, we could handle that. Good questions. So anything else on combustion? Yeah,
Sorry, one last question. That equipment that you got, that's the combustion lab that was formerly at the University of Utah.
that's correct.
You want to tell the story of how you got that? It's a good story.
Because you were very helpful in that.
Well, what that I was helpful. I'm gonna tell the story.
You tell us. Please do.
Stand up, you can't see you behind. Right here.
I have veto rights about what you say. Go ahead.
Always.
Go ahead.
I'm a lobbyist, you put a quarter in me, I'm gonna keep talking. No, very briefly, this was like 6 years ago or so. I got a call from Jordan Clark at the Office of Energy Development, who you had contacted, Dr. Pride contacted,
Right.
and said, hey, the University of Utah, in all of its wisdom, has decided because it really doesn't like carbon anymore, it has this great lab, has equipment that's so new it's under warranty still, they're gonna mothball it, they're gonna scrap metal it, which is crazy because that combustion unit is valuable for things, for projects like he's been talking about. And I was familiar with it because for years I've worked with a company called Redleaf Resources that is an oil shale producer, and Redleaf has used that lab to test how oil shale reacts to different heat and other stimuli. So it was like at least halfway through the sessions, and so it was past the RFA stage. But we dug in, we went to Senate leadership, we talked to Senator Hinkins, went to Senate leadership with the House leadership and said, this is crazy, don't waste this equipment. For a couple $100,000, you could move it down to where it would be loved and used and beneficial for a lot of different reasons, but we need the money. And the great thing about working in Utah is you can do good work in a short amount of time. So we got it down there and we got this metal from the UN sent down there so it wouldn't be scrap metal, which would be crazy. And now it's still a useful combustion lab. But I noticed though that some of that equipment's blue. And I'm wondering, did it get painted Aggie blue? Did it paint BYU blue? Because it looked a little BYU blue to me, but it's no longer red.
So I do have a couple of comments on that. It is an awesome story. You know, I was about the time that you got contacted about that through Jordan, I was running it the very final test in this piece of equipment. And I had partners coming in from Sweden, from Chalmers University, and we were doing some work for Pacificor, and all this group was together, and we're like, these data that we're getting are fantastic, and you can't do this anywhere else in the world. Why are we letting this piece of equipment go? And I was so busy, I was thinking, I don't need another thing to worry about, but we really need to keep this piece of equipment, and I'm so grateful for your help to make that happen. The cool part of the story is, Yeah, the equipment was dismantled and it got put on how many trucks? 5, 7? And it was hauled down there and kind of dumped in the yard. And then we hired an individual who used to be a coal miner. And I brought them a picture and said, here, build this. And it was like a puzzle. And he said, do you have drawings? Do you have fabrication drawings? No, here's your picture, build this. And so he did. It was pretty fantastic. So yeah, I appreciate the help that we've received to get that piece of equipment down there. It's unique. It's unique in the world. And that's why people from the UK come to use it. And right now I'm putting as much projects as I can handle, as my bandwidth can handle through that facility. And we're in the process of trying to get other people to bring in projects to go through facilities like that. It can be much bigger than just me. So I'm going to talk now just a little bit about gasification, and I'm going to go quick because I know you all want to hear about the new technology, not the caveman technology. Gasification is really useful, and it's important right now because the federal government's changed their interests with the new administration. And obviously they don't like fossil fuels very much, but they do like taking refuse materials and turning them into useful materials. That could be refuse coal, it could be biomass, it could even be municipal waste. And in order to do that kind of work and that kind of research where the dollars are available, we need gasifiers. And we don't have any at this facility right now. And so right now we are in the process of using some funding that we have and trying to find new funding so that we can build the gasification equipment there that's going to carry us into this avenue of research as well. And so we're building a new building. It's going to be right here. And in that building, we're going to split it up. And out here, we're going to put what's called a rotary kiln. And in here, we're going to put a gasifier. Now, these are two different types of gasifiers. We actually already have a rotary kiln. We got it from a local company. It just needs to be installed. It needs a home. Rotary kilns, you know about rotary kilns. You've seen them. They are at all cement plants. And really, in rotary kilns, we dump limestone into these things and it gets heated up. And it calcines and it forms lime, and that's what makes your concrete all stick together. So really, it's just a high temperature processing unit for whatever. This piece of equipment is the one that we just received that we need to install. And here's why it's exciting. We already have several projects lined up for it. We have one local company, Blue Sky Energy, who's commercializing coal to products. They need scale up support and they want it installed right now so that they can be working with us to get scale up support. We also have a company called Combustion Resources who's writing a phase 2 SBIR that needs this piece of equipment in order to be successful. And then Reaction Engineering International, the company that I used to work for, has 2 phase 2 SBIRs and 1 phase 1 SBIR to get money from the government to investigate biochar, refuse coal to products, and sustainable crops. And all those things are of interest. And out of those 5 or 6 opportunities, I guarantee several of them are going to get funded. So we need a facility like this. And then the last thing I'll say is that we need an in-train flow gasifier. This is like the new technology to convert solid and liquid fuels into gaseous fuels and other materials. And we're in the process of designing a facility like this and trying to find ways that we can raise money to build this piece of equipment. And this is a situation where if you build it, they will come. I've been in contact with the people at the Department of Energy who are in charge of the gasification technology for several years. They've been begging me to build a facility because they know how we work at the Centerville Energy Research Center, and they know they're going to get the stuff they want out of a facility like that if it's there. So I'm going to be done talking now, and you can hear from Matt and about nuclear. Yeah.
Can I ask just one question really quick? At Natural Resources, we had an RFA come through for $4 million for the Centerville Energy Research Center. And Greg Todd, he presented it and he did a great job. But I hope everybody can see how critical this facility is, this installation is. And as legislators, if you could, and as county commissioners, if you could maybe talk to some of the members of that committee and do your very best to convince them that this is not only good for Emory County, but this is good for the entire state. This is something that actually elevates us, elevates the state of Utah to a completely different plane when it comes to energy research. And it
Can I
puts
comment
us-
on that?
Yeah,
I think, well, I know, Utah has been a lead researcher in the world in combustion for many years. Both the University of Utah and BYU had the consortium of ACERC in place, and they were well known all over the nation and all over the world. We have not weakened any. We've just changed a little bit, and we broadened our interests. And we have power here in the state in combustion, in other fossil fuel technologies, in nuclear, in solar. We need to leverage that right now so that our country also knows that this is a powerhouse in energy, and that this is a place where money can be spent, where government funds can be spent in order to find the technologies of the future. And Emory County wants a piece of that because it really matters for their future. Because these power plants, Hunter and Huntington, have closure dates, and they wonder what's next. And they will participate because those transmission lines are very important, but they want to say in what happens. So this is an important facility.
let me just make the disconnect and then turn it over. But the disconnect is this, as when it comes to energy production in the state of Utah, we don't even rank in the top 10. When it comes to production of oil, gas, and coal from the state of Utah, we're not even in the top 10. When it comes to research, we're in the top 5. And so there's this disconnect that we have to figure out in order to leverage our resources, and all of these resources, the severance taxes, the royalties actually go to education and go to development to the full state. This is an important asset to the state, and I'll just shut up.
Absolutely. Matt, it's your turn.
Thank you. I have to be careful what I say about Andrew, because otherwise he'll show up with Nerf guns in my class today and blast me and it'll be a riot. So Andrew did a good job introducing just the situation for energy in Utah. So my background, I grew up in Centerville, Utah, and well, we used to go skiing all the time at
Back further than that, Matt, it's in Scipio.
my family comes from Scipio. That is true. My dad grew up in Delta. His dad was a renegade who left Scipio to go to Delta.
It's behind you.
Oh, sorry. Yeah, sorry. I'm gonna push the Zoom. But I remember coming home from skiing at Snow Basin once and seeing this when I was about 13. We're all familiar with this, right? I asked my dad, what in the world is this? And he explained to me, he was a oil and gas guy, and he explained about the inversion pollution, and I was fascinated. And from that point on, my goal was to learn about energy and pollution to make this problem kind of go away. So I did chemical engineering at BYU, studied lots from coal, oil, solar. Well, my last year at BYU, we had 4 scientists from the Idaho National Lab come down and teach an introductory nuclear engineering class. And I knew I was in trouble because it was a Friday night and I turned down my friends and my dates so I could stay home and read the textbook. That was a problem, but it was also a good thing. It let me know that there was a passion here, that there was a real potential for nuclear energy. So I ended up going to MIT and studying, getting a PhD in nuclear energy and nuclear engineering from MIT. After that, went to Westinghouse, had no intention of doing academia. I was going to go help design reactors. I did that for about 5 years, was involved with the AP1000 and the small modular reactor, which is a competitor to NuScale, which is up in Idaho, and you guys know about UAMPS. And about 5 years into that, BYU reached out and mentioned they were interested in developing nuclear expertise at BYU. So since about 2014, I've been at BYU doing nuclear engineering and nuclear energy research. So you guys are probably familiar with this considering the name of the committee, but I still want to give a little bit of a background before I get, oh, keep doing that. I still want to give a bit of background. I'm used to my classes where I go forward. Anyway, I still want to give a little bit of background about nuclear, just so you guys are on the same page of why I'm so excited about it. First of all, nuclear is incredibly energy dense. You get 10 million times more energy out of the same amount of material that you do from any other form of energy. And this is the appeal, right? That little pellet of uranium, which is about the size of the tip of your pinky, has enough energy when we use it as we do. It's about equivalent to about 3.5 barrels of oil, 17,000 standard cubic feet of natural gas, about 1,800 pounds of coal. So when I tease Andrew about being fat, part of it's just because of the difference in energy consumption here, right? But anyways, the best part is it's clean. There are no gaseous emissions at all. Okay. What a lot of people don't realize is nuclear is also highly reliable. We make 20% of our electricity in the US from nuclear, and it's been that way for decades. In fact, we had the governor of New Hampshire come out and visit BYU right after I started, and he told the story about how about 8 years ago, we had that huge cold snap in the Northeast, and they had feet and feet of snow, and the temperatures were sub-zero for days on end. And he said the only reason we didn't have rolling brownouts that would completely get rid of heating in that area was because they had that nuclear plant, a couple of nuclear plants in New Hampshire that kept the whole grid going because they run 90% of the time. Very safe as well. The big challenge that nuclear faces is it has the impression or the public perception that it's not safe. But a while back, somebody actually went through and assessed the data of deaths versus the amount of electricity produced. And they put together this table of deaths per year per terawatt hour of electricity produced. And the shocking part was that nuclear was at the very bottom of the list. The very least deaths. This counts Chernobyl, it counts Fukushima, it counts 3 Mile Island, it counts everything you can think of. Still, nuclear has the lowest death rate per terawatt hour. The reality is electricity is essential for our society, but there's also inherent risk associated with it, and nuclear does the best when it comes to keeping things safe. So I mentioned the always on. Another thing that people don't recognize, that I didn't even recognize until after I came to BYU, is that we have essential medicines that we only make from nuclear fission. In other words, we split that uranium atom and we get some radioactive isotopes that are perfect for looking inside of our body without cutting us open, because that would be less than ideal. And so we do 20 million procedures a year using these isotopes, but they only come from fission. And in fact, we don't have reactors in the US that are tuned to make those. We have power reactors, but to get the medical isotopes out, because they decay after 7 days, we have to constantly be shutting them down, chopping open the fuel, pulling out the stuff we need, putting the fuel back together, and then starting it up. We just never make power if we did that. And so we actually import all of our isotopes from the US. We are US. We import it from the Netherlands or from Canada, although the Canada plant shut down. And so there's also amazing technologies for treatment. I don't know how many of you guys are familiar with this. This was the biggest shock when I started looking into it. About 20 years ago, Sloan Kettering came up with a technology called targeted alpha therapy. And in essence, what they do is they make a smart cancer bomb. They take your natural antibodies, which are very good at finding cancer, and then they attach a radioisotope to it. And that radioisotope will go directly to the cancer and then fire off a particle and kill just the cancer cells. It is so safe, it is orders of magnitude less harmful than current cancer treatments. And in fact, they were able to apply it to kids who were about to die, and they had no collateral damage and were recovered within about 3 treatments. This was amazing. Well, why hasn't this been commercialized? Well, it turns out the isotope that is perfect for this treatment is only made using thorium reactors, which don't exist. We had one back in the 60s. Sloan Kettering used the leftovers from that reactor to do this study. It worked beautifully well, and we ran out of the stuff because we don't run thorium reactors anymore. We just had that one test. I'll get into that. It's a long background, I'm sorry. But I talk about the background here. Here's the crux of the matter. The nuclear that we have now is light water reactors. This was developed by Admiral Rickover with the Navy. It used lots and lots of water with solid uranium fuel, and it had great benefits. As I mentioned, really safe, lots of power, but it also required a lot of water. Not a big deal for submarines because they were surrounded by water. But we've seen in places like Fukushima, if we run out of water because there's an earthquake and floods and tsunamis that end up ruining our ability to pump water, then we might have some risks of overheating and causing some problems. It's also very good at making plutonium and weapons, which back at the day of the 50s and 60s was a desirable thing. Now it's a concern for all of us, particularly considering recent events. What a lot of people don't realize is at the same time that the US was developing these light waters reactors, they were also developing a different kind of technology down at Oak Ridge National Lab called molten salt reactors. And instead of having solid uranium with water cooling it off, they actually put the fuel, thorium in this case, directly in a salt. and a very high temperature, just like table salt, but a little bit different chemistry. And then they'd heat that salt up and melt. And the advantage was if you put fuel directly in the salt by its nature has very strong positive and very strong negative charges that stick around, and it wants to bind to everything. So if you stick uranium in there and start splitting the uranium, instead of worrying about all the radioactive stuff getting out, the salt binds to all of it and traps it in very effectively. In fact, we did some studies for the military. They want to know what happens if a missile strikes one of these salt reactors. And it turns out, have you ever seen the videos where they take boiling water in Minnesota and throw it in the air and it's frozen by the time it hits the ground? Same thing happened. It'd blow a hole in the reactor. You have the salt come out. It would freeze. It would trap everything in and just fall to the ground. And somebody could go vacuum up and you're done. There's no huge event. So very, very safe. No possibility for a meltdown. Just the way that it's configured, it's already liquid. And if things go wrong, it will freeze and lock everything in place. Doesn't make weapons very well. And they ran one of these for 5 to 10 years. And most of the problems we think of with nuclear, this type of reactor really addresses those issues. But it came to a point where the US government said, we can't fund both programs. It's too expensive. Pick one. Admiral Rickover was both well-connected and he had the ace in the hole that he could make a lot of weapons, which at the time is what we wanted. So we decided to pursue the light water reactor route. What we found in the recent years is that this molten salt reactor technology has incredible potential. And so we've been starting to pursue that potential. And in fact, at BYU, we actually developed a concept where we have a micro molten salt reactor. It's only about 5 feet by 7 feet for this core, but you can attach it to a turbine, control systems, power conditioning, and fit everything on a 40-foot truck bed. And this makes enough power to power about 10,000 US homes. So really incredible, highly power dense option. Really excited about the opportunities here. In fact, we licensed this technology to a company that I helped to start called Alphatech here in Salt Lake, and they are working to commercialize this reactor. Well, if it's so promising, why don't we have it already? Well, the big barrier to entry for all things nuclear is the federal regulation. The federal regulation is incredibly onerous and difficult to get through. When I was at Westinghouse, we were licensing the light water reactor, the AP1000. Any guesses at how long or how much money it took for that reactor to get licensed, just to get a license to operate it?
27 years.
That's very close. It was 20 years and $1 billion. Ridiculously expensive and ridiculously difficult. And that was just for a light water reactor that was a slight bit higher than the other one.
That was just for one permit.
That was one permit.
Yeah, you gotta have another officer.
Yeah, yeah. So it's a difficult process. Yeah.
So I might just need a number, but like, what does $1 billion with that kind of ramp up translate into per kilowatt hour?
So when you amortize that out, it's the biggest chunk of the costs, right? You're talking about 3 cents per kilowatt hour just for that part, right? And so that's the hard part. That's the part that's difficult.
Sorry.
You
told me to sneak behind you, then you back up just to be cold.
I walk too much, sorry. So, and that gets into what we want to talk about. The cost comes from, they've got to test every single piece, every single component. They've got to run experiments and they've got to validate that this is going to work. And a small fraction of that is even the nuclear part. Most of it is looking at things like, how well does this pump work? How long will it work? What happens if it fails? And they've got to do that for every piece and then group of pieces. And by the time you add all of that up for a massive complicated plant, you're talking about $1 billion just in tests and experiments and analysis. Not to mention that you have to pay the NRC to tell you your design is not good enough, but that's a different issue that we'll get into later. The advantage of these micro salt reactors is already they're inherently simpler and safer than the large light water reactors, which are already incredibly safe. And so the idea is that you could possibly license these faster. Not only that, they're capable of making, because they have that liquid fuel that we can access easily instead of uranium that's trapped in fuel rods, that's trapped in a pressure vessel, that's trapped in several layers. So you could actually pull out medical isotopes while it's operating and make both electricity and medical isotopes. So it's a really incredible technology that we've been excited about. But the question is, how do we get it licensed? And just like the light water reactors, there's a lot of tests, only a small fraction of which need to be done. And this is where the San Rafael Energy Research Center comes in and really shines. And we've already had some pretty incredible successes that I'll talk about. A couple other advantages here. Andrew talked about the Brayton cycle. We're really excited about him developing the Brayton cycle so we can use it later. Because of the fact that the temperature is higher. When you're dealing with water, you're limited to how high you can go in temperature, because otherwise the water will boil and get to the point where it's not useful. If you're using the Brayton cycle, you're using gas and you can go to much higher temperatures. And so we've looked at his Brayton cycle and done some studies on that and found out that if we use the Brayton cycle, we can generate electricity. And when we're done making as much electricity as we can make, the gas coming out of that Brayton cycle is still at 500 degrees C, which is hotter than most power producing outlet temperatures. And so we can take that leftover heat and we can do a ton of things with that heat. One of the things we looked at is water production, and I'll talk about that in a little bit. But another thing is, not only can we pull out medical isotopes, we went through and found out that of all the leftover pieces of that uranium splitting, we have huge amounts of rare earth elements. If we were to produce equivalent of like 5 different reactors that currently operate worth of molten salt reactors, we could pull out kilograms of things like europium, neodymium, all kinds of valuable rare earth elements, part of this salt extraction process that we developed at BYU. You can also look at things like making graphene from your coal. So you'll never get retired. You'll just switch from power to other things. Making graphene, making nanotubes, making all kinds of coal products. The technology for this already exists. Why don't we do this with our coal? It's a cost thing. It costs way too much money to get the heat necessary to go through these processes. Well, if you have a reactor that's making electricity and the leftover heat is really high temperature like this, as a byproduct, you can start running these processes and that makes it much more economical. You're getting your money out of the electricity. And by the way, you're making these products on the side. So it opens up a lot of doors when you combine the coal and the nuclear technology like Andrew was talking about. Now I mentioned water desalination. This is a big issue now. So we wanted to look at this and we've done some exploring. We did some simulations and figured out that if we were to get 86 of these small modular reactors that we developed, and you were to make the electricity and then use all of the waste heat to do desalination, and you were to run these full time down in southern Utah, we could fill Lake Powell from bottom to top in about 14 months, assuming we had a source of water to desalinate. Turns out we do have quite a bit, and I'm sure that Steve Lund has talked about that a little bit to you guys. So where does this fit in with the SRERC? Andrew mentioned this already, and the pictures are, of course, in the wrong order, but we'll look at it anyway. So that's the site. He talked about these buildings, this one and the one's going to be built. We're actually in that main building there. And what we've done is we've set up a lab that's not going to be looking at all the nuclear fission and things like that. Remember, I mentioned about 90% of the tests have nothing to do with the fuel or the waste or anything radioactive. It's questions like, how is the thing going to work? One of the biggest questions is, how do we make the salt? How do we keep it from corroding everything? When they did that test back at Oak Ridge, that salt, the positive and negative ions worked really well for trapping in radioactive waste, but the problem was it also meant it wanted to corrode everything it touched. And they didn't get to the bottom of that. They just said, well, we're just going to replace components every 5 years. That's not terribly economical. So one of the things that we did is we set up a lab at Centerville Energy Research Center to look at the corrosivity of the salt. How do we clean it up so it doesn't corrode through everything? As an example of one of the successes. By the way, when we talk about interest at the San Rafael Energy Research Center, I want to give just a caveat, or not a caveat, a clarification. There are dozens of companies that want to license these molten salt reactors.
Dr. Memo?
Yeah.
Can I interrupt you for just one
Please
minute? Because
do.
I think there's a few of these guys are going to be taken off here in just a second. We've got the room for a bit, so I don't want to,
Yeah.
I don't want to stop the.
Sorry, I'll talk for hours. So
No, and we would listen for hours too, but we have a special guest. She's an influencer here. Senator Reeve.
Oh,
There's your yellow cake, but you have to wear it, so. Okay, all right. I want to, you gotta take one too.
thank you.
There's Dr. Fry. Anyway, I got a few more here. And we are going to do this letter. John, I don't know if you need to talk about, I talked about a little bit at the beginning. So I've got a letter to the governor, just saying kind of what we talked about a couple of weeks ago about the water issue. I can send it around to you, but I did want to get kind of an official position. We haven't ever issued anything from the Yellowcake caucus, but I want to issue this letter from the Yellowcake caucus. Is there anybody opposed to that? Okay, I'm gonna go ahead and sign it, and I'll send it out to you. It's nothing other than saying we want to manage our forest for water efficiency. John?
Go ahead and I can ask words if people are around.
Okay, I know there's some appropriation meetings are going to be starting up, so I didn't want to miss these guys before I cross that little bit of business. I also felt this say hi to Bob and Elaine Berry. They're friends of mine from down in Monticello, soil conservation. Most of you know Bob, so glad to have them here. Anyway, back to you. Matt.
Thanks. Well, let's not take too much time. Let's get down to the nuts and bolts of this. The point is there are dozens of companies that are very interested in developing salt technology because of the benefits that I just outlined. That's why I gave that background so you could see the big picture. And they are all over the country, and their interest in answering these key questions is high. Some of them, like Kairos Power, which is founded by Silicon Valley, very rich people, have the funds to build facilities everywhere, and they're doing that. Some do not. But all of them are very interested in these issues. In fact, we put a team together that includes Kairos and Alphatech and BYU and a couple of other companies to say, okay, let's look specifically at this salt issue, this corrosion issue. How can we get the salt so it won't corrode everything? Because that's been considered for the last decade the holdup to being able to make these really affordable and reasonable. And so we got this team together and we put together the research down at the San Rafael Energy Research Center and started investigating the salt. And the issue is the salt that almost everybody uses is called FLiBe. It's a mix of fluorine, beryllium, and lithium, as you see. When it's clean, it looks like this, but if we buy it from the suppliers, we bought some from Materion and a couple other people that make the two different pieces, lithium fluoride, beryllium fluoride. You mix them together, and by the time you stick them in your little nickel crucible and melt them down, it starts to turn from this nice clear liquid into tar. It just gets black and gross because it's corroding everything. And so we studied how we could get that clean, and using the facilities down at San Rafael Energy Research Center, we compared it to what's usually done. Usually what they did at Oak Ridge is they'll bubble HF gas, which is highly reactive, highly toxic, highly problematic, through the salt, and that fluorine will take the extra impurities out. What's left behind is a lot of hydrogen. So we looked at a different approach, and we looked at using electrochemistry, using the facilities at the lab. Long story short, I don't think this worked because Andrews didn't work. But if you look here, there's a little nickel crucible, and inside you can see some salt that looks like tar. That's what it looked like when we got it from these people who had cleaned it using the HF method. Well, with the technology we developed at the SRERC, you look right there, it looks like boiling water. In fact, we did a comparison. We tested their salt that was clean compared to the salt we developed at SRERC. And we poured them into these nickel crucibles, and we watched as their salt started turning black into tar, and our stayed as clean as water for days. And so in essence, we've gotten to the point where we've been able to fix this corrosion issue, and Kairos and other companies were just ecstatic. We just called them yesterday, in fact, and they were really excited about the fact that this big issue that they needed solved with work at the Energy Research Center had been largely resolved. And that was a matter of optimizing and categorizing and figuring out how to commercialize this. And so the Energy Research Center, not only is it doing great things for coal, but it's answering the questions that the nuclear companies need answered to be able to license these reactors better, faster, and more effectively. And that work has already taken place, and we've already seen success with that. Oh, that's good work. Yeah, I don't know if you can see that very well. It's kind of small, but it looks like tar boiling in there. And then after we went through our process, you can see the one on the right, it looks just like water. And the big part of that is it didn't corrode anything once we got that out. Basically, the hydrogen and oxygen left over were the problem. And we figured out how to pull that stuff out. And that all took place at the SRERC, at those facilities down there. Having those glove boxes and those qualification instruments made it possible for this to happen. That was some innovation. And now all the companies are really excited about the possible things that are coming out. It really put the SRERC on the map in a way that now all the big nuclear companies are aware and interested in coming and participating, so long as we have the funding to be able to continue to have the equipment that they need. So long story short, really long story short, nuclear is a great way to go for energy. I really think it will be the future, combined with other things like coal and some of the other renewables in certain circumstances. Molten salt reactor technology is a step ahead in all the things that we care about. And so a lot of people are working to develop that. And the SRERC is really positioned to be an instrumental key piece of developing the salt reactor technology. And we'll put Utah on the map for being a lead in energy technology, rather than just not even the top 10, as Representative Love mentioned. So with that, sorry to go a little bit over. I'm done. You can ask Andrew questions.
Well, thanks, Matt. Really appreciate that. It's so good. I have to just show you one This is what I got last night. It's a new little granddaughter, so. My daughter Brooke helps me with a lot of stuff, and she texted me at about 8:20 last night, and I said, Brooke, aren't you supposed to be having a baby right now? About 9 o'clock, she sends a picture of the baby, so that's how dedicated she is. 16 grandkids. Wow. She's a nurse. I said, Brooke, you know what causes this, right? So anyway, I'm glad to have John here, and so John, will you just take a few minutes and give your spiel? If there's anything else I'm forgetting, remind me, but
I'm sorry, you had me on the agenda early and I got here late. I apologize.
it's tough to get here.
It's I had a telephone call just as I was walking out the door, and unfortunately that's what happens. But I appreciate it. You were among the first to see that letter that Councilwoman Theodore sent to the governor and others, and we had a nice conversation a couple of weeks ago, and we've been approached by a number of other people who would like to sign on it to a letter to encourage the governor and leadership to do some things. And so this offered me an opportunity to come and say, you know, if you're interested, we'd be happy to have your support and appreciate it. And I think that's just fine. And if you have any questions, I'd be happy to pick them up, but I'm not don't have we had a nice conversation with the county council earlier this week on Tuesday, and you never have everybody thinking along exactly the same lines, but that's a good thing. It's nice to be able to hear the different sides. So anyway, I'd be happy to entertain any questions if you have any. Otherwise, see me afterwards and we can chat. Thanks, Phil.
Yeah, thanks, John.
Yeah, go ahead.
There's quite a few people that have expressed interest in having their names at the letter, as well as farm bureaus and other organizations. But I saw the list of people who had made it onto the list, and a lot of people who thought they were on the list weren't on the
Okay.
list. So if you could ask the people that are here today, if they want to be on the list, to confirm with you and physically or text or whatever,
Yeah.
give you their name and their permission to make sure that they are added on the list. Because I think a lot of people just assume that they would be, and then.
And the issue is, we wanted to be sure that we wanted to confirm with everyone before your names went on the list. We don't want to put your name on a list and then have you be upset. So, yeah, that's great. I would love if you would contact me. Let me give you 2 ways you can take. If you want to text me, it's 801-558-1347. That's 801-558-1347, or you can send it to my email address at Salt Lake County, which is J.O. Bennett. That's 2 N's, 2 T's, 2 E's. The E's aren't together and only 1 B. And then at slco.org. So, and or you can see me afterwards, and I'd be happy to take your name, and we'll make sure that if you're comfortable with
And I
that.
have your contact info too, if somebody is wants to.
Yeah.
Hey, so let's send me down.
Yeah. Okay, well, great. Thank you.
Thanks, John. I do want to thank Celeste for helping on getting some signatures. I thought maybe I'd get a few signatures, and I sent a thing to Celeste, and next thing I know, my phone's blowing up and she's out gathering signatures, but it's really good. Now I think we're gonna end up with about 170 or so signatures on that letter, which is good. And the nice thing about this letter is the governor really supports this effort. He had kind of indicated if it wasn't to him, he would probably sign the letter himself. So it's not a fighting letter at all. Heath Hanson's here with Senator Lee's office. Thanks, Heath, for coming. Representative Cotter came in a little bit later, so glad to have you here. Anyway, I think that wraps it up. Unless anybody's got questions, feel free to hang around and visit. We've got this room for another hour, I believe. So.
Yellow 2 weeks in a row for you.
Oh, for the Yellowcake. Thank you. Yeah, go ahead. Well, thank you all very much. Thanks for our guests for coming. Really appreciate it.